Now let's discuss the example scenario 2, which requires double rotation after a node deletion to restore the balance factor in the subtree. The difference between this scenario and the previous one is that here the LGC is a leaf node, that is, it does not have any child. RGC has two children, C and D. Due to this, the height of RGC is greater than the height of LGC and LC is right heavy. We want to delete the node X from this AVL tree. As earlier, the HT over every node shows the height of the node. The height of node P is 3. As discussed, we find and delete the node X as per the BST delete procedure, and the resultant tree is shown on the right. As we know, due to the deletion of a node, the balance factor violation may be generated anywhere upwards in the tree starting from the parent of physically deleted node. Hence, we check the balance factor at these nodes. The balance factor of RC is 0, but the balance factor of P has become plus 2. Hence, we need to do appropriate rotation to restore the balance in the subtree. The immediate question is, which type of rotation should be carried out? P is left heavy as the height of LC is more than RC. Further, LC is right heavy as the height of RGC is more than LGC. As P is left heavy and its left child LC is right heavy, this is the left-right case. So, a double left-right rotation at P is required to restore the balance factor in the permissible range of -1 to 1 in the subtree. The double left-right rotation is a two-step process. Step 1 is the left rotation at LC, and then step 2 is right rotation at P. Let's discuss the step 1, that is the left rotation at LC. As mentioned on the slide, RGC moves upwards and LC becomes its left child. Note that this rearrangement does not violate the binary search tree property, as the value of LC is less than the value of RGC. Now we need to adjust or shift the left subtree of RGC. In this case, the left subtree of RGC has only one node C. As per the BST property, value of C is greater than LC and less than RGC. So, it can be attached on the right of LC without violating the binary search tree property. The resultant tree is mentioned in the middle of the slide. Let's now discuss the step 2, that is the right rotation at P. As mentioned on the slide, RGC moves upwards and P becomes its right child. Note that this rearrangement does not violate the binary search tree property, as the value of P is greater than the value of RGC. Now we need to adjust the right subtree of RGC. In this case, the right subtree of RGC has only one node D. As per the BST property, value of D is greater than RGC and less than P. So, it can be attached on the left of P without violating the binary search tree property. The resultant tree is shown on the right slide. We note that the balance factor of all the nodes have been restored to the permissible limit of -1 to 1 after these rotations. The new root of the subtree is RGC and its balance factor is 0. The RGC height is +2. In this case, the height of resultant tree is decreased by 1. This may generate balance factor violation further upwards in the tree, which is required to be checked and adjusted. Let's now formally show that the double left-right rotation restores the balance factor in the left-right case. Consider the symbolic tree on the left in the slide. Here, a circle represents a node and a rectangle represents a subtree. Left child of P is LC and the right subtree of P is RC. Left subtree of LC is named as LGC and the right child of LC is named as RGC. LGC is the acronym for left grandchild and RGC is acronym for right grandchild. Assume that node X was deleted from the subtree of RC and its height got shrunk. When we walk upwards in the tree starting from the parent of the physically deleted node, P is the first unbalanced node in the tree and its balance factor is +2. Let the height of LC be h+1. As the balance factor of P is +2, the height of RC is required to be h-1. Further, the height of P is 1 plus maximum of h+1 and h-1. So the height of P is h+2. As we are considering the left-right case, we assume that P is left heavy and the left child of P, that is LC, is right heavy. That is, height of RGC is greater than the height of LGC. As the height of LC is h+1, the height of RGC is required to be h, and the height of LGC is h-1. The height of LGC cannot be less than h-1. Otherwise, a balance factor violation will be generated at LC, which is not the case here. As the height of RGC is h, one of its children, A or B, must have height h-1. The other child can have height h-1 or h-2 without causing the balance factor violation at RGC. When we do the left rotation at LC, the RGC moves upwards and LC falls on its left. Note that this rearrangement does not violate the binary search tree property, as the value of LC is less than the value of RGC. Now we need to adjust left child of RGC, that is subtree A. As per the BST property, the value of A nodes are lesser than RGC and greater than LC. So they can be attached on the right of LC without violating the binary search tree property. The resultant tree after the left rotation at LC is shown in the middle. As earlier, the height of LGC is h-1. The height of A is either h-1 or h-2. Height of subtree B is h-1 or h-2 and height of RC is h-1. After rotation, the new children of LC are LGC and A. The height of LGC is h minus 1 and that of A is either h minus 1 or h minus 2. So the height of LC is h. The new children of RGC are LC and B. The height of LC is h and the height of B is h minus 1 or h minus 2. Hence, the height of RGC is h plus 1. The new children of P are RGC and RC. The height of RGC is h plus 1 and height of RC is h minus 1. Hence, the height of P is h plus 2. As this is the intermediate stage of the two-step rotation process, the balance factor of nodes is immaterial. The step 2 of double rotation is right rotation at P. When we do the right rotation at P, the RGC moves upwards and P falls on its right. Note that this rearrangement does not violate the binary search tree property as the value of P is greater than the value of RGC. Now we need to adjust B, the right subtree of RGC. As per the BST property, the value of B nodes are greater than RGC and less than P. So they can be attached on the left of P without violating the binary search tree property. The resultant tree after the right rotation is shown on the right. As earlier, the height of LC is h. The height of B is either h minus 1 or h minus 2 and the height of RC is h minus 1. After rotation, the new children of P are B and RC. The height of B is either h minus 1 or h minus 2 and the height of RC is h minus 1. So the height of P is h and its balance factor is either 0 or minus 1. The new children of RGC are LC and P. The height of both these children is h. Hence the height of RGC is h plus 1 and its balance factor is 0. Before rotation, the height of subtree was h plus 2. After the rotation, the height has reduced by 1. This decrease in the height may introduce the balance factor violation further upwards in the tree, which needs to be checked and restored.